Okay, this is the second of two parts of the discussion of binary eutectic microstructures. In particular, we were looking at an example problem with a lead tin system, and we'd already looked at the case where the initial the system composition was less than 2 weight percent tin. We'd also looked at the case where the composition of the system was 10 weight percent. So we're not going to consider those any further. We're going to look at two a little bit more interesting cases now. One where we have the system composition the same as the eutectic composition, so and that would be 61.9 weight percent tin, and then one in the case where we have a composition of 40 weight percent tin. So we're going to start off looking at the system composition that equals the eutectic composition, so that's 61.9 weight percent. We're going to consider the easy case first, which is this location here in the liquid regime. Uh, Obviously, there's only one phase present, so we can write that the composition of that phase is going to be the same as the system composition, which we know is also the eutectic composition. And so we would write that as 61.9 weight percent. And then obviously the weight fraction of liquid it's 100%, so it's just 1. And if we were to draw that microstructure, it would just be L. Okay? So now let's go ahead and proceed to a little bit of a more interesting case, and that is the eutectic, crossing the eutectic point on cooling. And we're just going to go just ever so slightly below the eutectic point, so we get all the liquid out, we go to a complete solid solution. We're going to handle this the same way that we've handled all the other problems. We've already got a tie line, right? And that tie line is, in this case, the eutectic line. It sits across like that. And so we've projected the tie line intersects alpha at 18.3, intersects beta at 97.8. So we can just look at the tie line and write down the composition of these two phases, alpha and beta. The composition of alpha is going to be 18.3 weight percent tin, and the composition of beta is going to be 97.8 weight percent tin. Okay, so we can use these quantities now in the lever rule to figure out the weight fractions of each phase. So let's go ahead and do the alpha. So the weight fraction of alpha is just going to be, let's see, 97.8. So that's this location minus the system composition, so minus 61.9 divided by 97.8 minus the alpha composition, which is 18.3. And if we plunge that into our calculator, we end up with an alpha composition of about 0.45. And if we look at that, we can see that, just a gut check, that the eutectic composition is a little bit closer to beta and a little further from alpha. So we expect the alpha weight fraction to be a little bit less than half, which it is. So there's a little, at least a sanity check there. And then we could compute beta in the same fashion, or we can just recognize that it has to make up for whatever alpha is not. And so 1 minus what we just computed, W of alpha, and we now have that weight composition is at 55%. Okay, so we have a liquid that went effectively instantly to alpha and beta. And so we want to ask the question, so there's our structure. It's all solid. What does this look like? Because we don't have the case like we had in other systems where we had, or we even would have in this system, where we have a little bit of solid nucleating, and that solid, the amount of solid that nucleates slowly gets bigger and bigger until we end up with grains. We do still have grains, but how do we accommodate the alpha and beta emerging at the same time? So that's what we want to talk about here going forward. Okay, to think about the microstructure that's going to emerge, let's think about what we are starting with. So we're starting with a liquid. So remember what we're doing. We're cooling down through, cooling down through the eutectic point. Okay, so we begin with some liquid call it CL, that is 61.9 weight percent tin. And I'm going to go ahead and write the other portion of that. The other portion of that is that it's going to be 38.1 lead. Okay, that's going to need to split into an alpha phase that is roughly 18% tin, which makes this 82% lead, and a beta phase, which is about 98% tin, which makes it only 2% lead. Okay, so hopefully what you're thinking is, well, how can I take something that has 61% or 62%, let's say, tin, and now I have to create two phases, one at 18%, one at 98%, and then the lead, the alpha has 82% versus the 38.1 of the liquid. How can we do this? Well, hopefully you're seeing that what's required here is diffusion. And it's significant diffusion. Okay, so we need to diffuse, in this case, we need to diffuse lead to alpha, right? So we have more lead, and we need to diffuse tin to beta. But that's the diffusive processes that need to occur. So what we would actually draw to make this microstructure is there's the grains still exist, but it actually forms a lamellar microstructure. And the red that I'm coloring here is the alpha. So what this is two phases in the same grain, right? So and then we can go ahead and draw some other. So something like this would be an example of the microstructure that emerges, where the red would be the alpha and the white would be the beta, and they would have the compositions that we'd already talked about. So this is called the eutectic microstructure. Okay, so let me show you an example of what that looks like in a real material. On the right, you're looking at an actual micrograph. So this is a real micrograph. And on the left is just a schematic of what's happening. In this case, it's going the other direction. We're actually melting, so we're sorry, we're not melting. We're trying to grow the solid into the liquid, and that requires, as we said before, lead, is shown here, diffusing into alpha, and tin diffusing into beta. So we're trying to do that. And the lamellar structure facilitates that diffusion path. For our last example of this system, we want to look at the composition of 40 weight percent tin. So let's go ahead and again do the easiest one first. So we'll call this 0.1. At 0.1, we just have all liquid, and the composition of that liquid is 40 weight percent tin. Okay, the weight fraction is obviously equal to 1, and we can draw that microstructure just as all liquid. Okay, so now let's go ahead to 0.2. We'll call that there. So at state 2, we're just above the eutectic line. And what we're going to look for here is we're going to go ahead and do what we typically do. We'll draw our tie line through this point. Okay, and I'm going to go ahead and call that let's I know it's not perfect, but let's call it 60 weight percent, and we'll go ahead and call this 15 weight percent there. And if those are our compositions, we could write that we have the composition of alpha is 15, weight percent 10. I'm not going to write the units, but that's what the units are. And here the composition of the liquid is going to be 60 weight percent 10. And we can compute the weight fractions of each, just as we've done before. In this case, we'll go ahead and do alpha first. So the weight fraction of alpha is just going to be 60 minus 40 divided by 60 minus 15, which gives us 0.44. And we could then say that the weight fraction of the liquid is going to be equal to just 1 minus the weight fraction of alpha, which would be 0.56. And so we have 44% alpha and 56% liquid. So if we draw that microstructure, that's also pretty easy to draw. We'll go ahead and there's our alpha grains. I'm going to go ahead and color them red because that's what we've been doing before. So there's alpha. So there's liquid. There's alpha. And so that's all that we would need to do for that point. Now the question comes, what about when we drop down to just below the eutectic? So let's go ahead and think through that problem. Okay, so let's recall the microstructure we just got done doing. This was from point 2, which was just right above the eutectic line. So there's point 2. Now we want to ask the question, what happens here at point 3? So at point 3, we do the same thing we've always done. We go ahead and we draw a tie line, which now is just the eutectic line. And we can just read off that tie line the composition. So we have the composition of alpha is equal to 18.2 weight percent 10. And then the composition of beta is going to be 97.8 weight percent 10. And we can use this along with our composition of 40% to compute the weight fraction. So we'll go ahead and do that and write that the weight fraction of alpha is just going to be 97. Let's erase that. 97.8 minus 40 divided by 97.8 minus 18.2, which when we do the math on that comes out to be 0.73. So it's 73 weight percent alpha, and then we can compute beta is just as 1 minus W of alpha, which comes out to be 0.27 weight percent 10. Okay, so now we need to think through what the microstructure looks like. So I drew the microstructure for 2 because it's important for how the rest evolves. As we cool off, let's say right above the eutectic, we have roughly a microstructure that I'm showing in 2 here, but the liquid is almost, so it's right there, right there. The liquid is very near the eutectic point. So what happens during the transition is that the liquid portion goes through the eutectic transition and creates a eutectic microstructure. So the microstructure that emerges in this problem is what we showed here from 2, except now we replace the liquid with a eutectic microstructure. So let's see if we can do that. Okay, so I'll try to draw it as closely as I can to what I drew up there. And looks like a kidney bean there, and then something like that. Okay, so there's what existed as alpha before we crossed that eutectic line on cooling. So now we can say, let's go ahead and make a few grains here. I'm gonna draw these as grain boundaries. And then inside these grains, we're gonna have a eutectic microstructure that comes about, just like we had talked about on the previous example. Okay, so I better make my grain go here. And so this particular microstructure could look like something like this. Okay. And then we can have one that maybe is vertical, for example, here on the microstructure. Okay, so that's the microstructure that we have. The new definition that I want you to be aware of is that we now separate out and we talk about in two different steps or two different terms. The alpha that resides in the eutectic, that's so the alpha in the eutectic microstructure. Whoops. Let's write that better. Eutectic microstructure. That's just called eutectic alpha. Okay, and I'm going to use a different color. Let's say blue. So now this is the pointing to the region that existed before the eutectic transition. So the alpha that was prior to the eutectic microstructure, that's called primary alpha. Okay, and we could do the exact same thing if we were on the beta side, although obviously we don't have very much room to work on the beta side, but the same features, we could have primary beta if that was something that had formed before a eutectic transition had occurred. So that covers all that you really need to know about the eutectic microstructures that emerge, and the main four cases that kind of cover all of the possible configurations that we could have.